Hey, welcome to The Explainer. Today, we're going to do something pretty incredible. We're going inside the most complex machine on the entire planet, which is you. We're going to explore the amazing engineering that's happening inside every single living thing, from the basic materials that build us up to the super smart systems that keep us safe.
So, have you ever really stopped to think about it? What does it actually take to build, power, and defend a living organism? Well, in this explainer, we're going to break down that blueprint of life into three core parts: the building blocks, the power source, and of course, the security system. So, let's kick things off with the raw materials.
First up, the materials. To build something as ridiculously complex as a living thing, you need a seriously versatile and powerful toolkit. And at the molecular level, all life is built from just a few key types of really big molecules. They're called polymers.
Okay, so what's a polymer? The easiest way to think about it is like a long, intricate necklace, a really, really long necklace. The polymer is the whole chain, and the individual beads that make up that chain, those are called monomers. And by linking these simple little monomers together in all sorts of different ways, life can create this just astonishing variety of complex stuff.
Now, of all these polymers, there's one that is the absolute MVP: proteins. These are the true workhorses of the cell. They're made of monomers called amino acids, and these are the versatile little machines that do pretty much everything you can imagine. We're talking billions of proteins in a single cell, and each one has a very specific job, from building your muscles to making chemical reactions happen at lightning speed.
So what's really fascinating is where a protein gets its power from. It's not just some simple chain. As you can see, that chain starts to coil and fold into these increasingly complex 3D shapes. And here's the kicker: that final unique shape is everything. It's what determines the protein's exact job. If you change that final fold just a tiny bit, it could be the difference between an enzyme that perfectly digests your lunch and one that does, well, nothing at all. Form truly dictates function here. All right, so to round out our molecular toolkit, you've got proteins doing all the work, carbohydrates like glucose as the quick-burn fuel, and then lipids, fats for long-term energy storage, and building things like cell membranes. But even the best materials in the world are totally useless without a power source. And that brings us to the engine room of the cell. Okay, so this brings us to the second major part of our blueprint, the cellular power plant. This is where that fuel we just talked about, mostly glucose, gets converted into usable energy to run every single thing your body does. Now, the goal of this power plant isn't to burn fuel for heat, like some old steam engine. Nope. It's to generate massive amounts of a very specific, high-energy molecule called ATP. And you gotta think of ATP as cash. It is the universal energy currency of life. If a cell needs to contract a muscle, send a nerve signal, or build a new protein, it pays for that job with ATP. So how do you make all this ATP? Well, the process is called aerobic respiration, and honestly, it's like a super efficient three-stage assembly line. First, glycolysis literally splits a glucose molecule in half. Then, inside the mitochondria, the citric acid cycle completely dismantles what's left, charging up these little energy-carrying molecules. And finally, those carriers power the electron transport chain, which uses oxygen to produce a massive energy payoff. It's a total masterpiece of biochemical engineering. And the payoff? Well, the payoff is huge. Get this. For every single molecule of glucose that goes into this assembly line, the cell gets a net gain of about 32 ATP molecules. That is a fantastic return on investment. But, and this is a big but, this incredible efficiency depends entirely on one crucial ingredient: oxygen. So what happens when it's not there? You know that feeling when you're sprinting and your muscles are just screaming for air? That's when your body has to switch to its backup generator, anaerobic respiration. The problem is this backup generator is a real gas guzzler. It only produces a measly 2 ATP for each glucose molecule, and it creates a byproduct, lactic acid, which is what contributes to that muscle fatigue and burn you feel. It works in a pinch, but it's definitely not a long-term plan. All right, so we've got the materials to build the machine, and we've got the power to run it. But this amazing, complex system is under constant threat. So how does it protect itself from all the microscopic invaders out there, like bacteria and viruses? Well, this is where the molecular security system comes into play. The entire immune system, the whole operation, is built on one simple but absolutely brilliant idea: telling the difference between self and non-self, or, friend and foe. Your own cells have these molecular ID cards called antigens that basically say, hey, I belong here. Invaders, they have different foreign antigens, which immediately flag them as a threat and trigger the alarm. Okay, so say a barrier like your skin gets breached. Who are the first responders on the scene? That would be your general security guards, the phagocytes. These cells are incredible. They're basically the Pac-Man of your body, moving through your tissues, just gobbling up and digesting any foreign invaders they find. But, for a more serious, sophisticated threat, you can't just send in the general security. You need to call in the special forces. And that's where lymphocytes come in. Unlike the phagocytes that attack just anything foreign, each lymphocyte is highly specialized. It's trained to recognize and take out just one specific type of enemy. And one of the key weapons these special forces use is the antibody. It's this cool Y-shaped protein. And you can think of it like a highly specific smart tag, or even a guided missile. Each antibody is built to lock onto one and only one specific foreign antigen.
And their mission is brilliant in its simplicity. First, the arms of the antibody physically grab onto the invader. This can actually block the pathogen from infecting your cells all by itself. But second, and this is so crucial, by binding to it, they mark the pathogen. It's like painting a giant glowing target on it, making it absolutely impossible for the cleanup crew, our Pac-Man phagocytes, to miss. But the immune system's most amazing feature isn't just that it can fight. It's that it can learn from its battles. It remembers its enemies. And this, my friends, is its ultimate upgrade: immunological memory. Think about the very first time your body sees a new virus. The immune response feels kind of slow, right? That's because your special forces, the lymphocytes, have to identify the enemy and then build up a big enough army to actually fight it. And during that delay, the pathogen gets time to multiply, and that's when you start to feel sick.
But this is where the magic happens. After that first fight, your immune system doesn't forget. It creates memory cells. And as this chart shows so clearly, if that same pathogen ever dares to invade again, the secondary response is overwhelmingly faster and stronger. The army is already trained and ready to go in an instant. And that right there, that's immunological memory. It's why you rarely get sick from the exact same cold virus twice. And it's also the fundamental principle that makes vaccines so incredibly effective. They basically introduce your body to a harmless piece of a pathogen, letting you build up all these memory cells without ever having to fight the real war. Your body is prepared for the battle before it even starts. So there you have it, the blueprint of life. It all starts with a common toolkit of molecules to build everything. Then you've got this sophisticated power grid to fuel every action. And to protect it all, an intelligent, learning security force. It is an interconnected masterpiece of engineering, and it's happening inside you right this second. So the real question is, what part of this incredible system do you find the most mind-blowing?